Okay, hello all. So I'm going to do a walkthrough, talk about section 2.1 to show you how you can get to my slides. If you click on my unit 2, it's not an assignment yet, but you should be able to get into my unit 2. And then once you wait for it to open, which might take it a second, and wait for the files to come up here, that you have section 21.rmd here, that if you click on it, it comes up here, and so you can see the code of how I created all of the slides here. And then if you click on run presentation, you'll see the slides that I'm going to be showing you here. Okay, so section 2.1 is talking about probability and outcomes. So some of the concepts that you want to understand here: the outcomes, probability, sample space, event, discrete random variables, continuous random variables. So we're going to start just to have a simple way for talking about probability, flipping a coin. So you can think of when you flip a coin, a heads is 1, a tails is 0. This is in some places referred to this as a Bernoulli distribution. R calls it a binomial distribution. Those two terms are interchangeable. So when you have a binomial distribution, you have either 1 or a 0. That's your sample space. Those are the possible outcomes. So a sample space refers to the possible outcomes. With a binomial distribution, the possible outcomes are a 1 or a 0. And we'll get a 1 p% of the time, and a 0 1 minus p% of the time. If your coin is fair, you're going to get p equals 0.5. 0.5% of the time, 50% of the time, 0.5. You will get heads. 50% of the time, you're going to get tails. So R has this R binom function that we can use to simulate having a binomial. We can simulate flipping a coin, right? So the I binom function takes 3 arguments. 1, how many triers are you going to do? 2, how many coins are you flipping? So how many coins are you flipping? Are you flipping 1 coin, or are you flipping 10 coins? And then you could, flip 1 coin, but flip it 10 times. That is how many trials you're doing. And the last one, is it a fair coin? That last one is P, the probability of getting heads each time. So if it's a fair coin, the probability of getting heads is going to be 50%. So our question is if we flip 10 coins, how many would you expect to be heads? So think about this for a second. If we flip 10 coins, how many times would you expect to get heads out of those 10 coins? Right. So what's the sample space if we flip 10 coins? The sample space is how many times do you get heads. So you could get heads 0 times, you could get heads 1 time, you could get heads 7 times, right? 0 to 10 is the sample space. It's the possible outcomes. Will the result be discrete or a continuous random variable? We'll see. The outcomes can be 1 heads, 2 heads, 3 heads. For it to be a continuous random variable, you have a continuous random variable if between any 2 results, there is another option in between those 2, right? So if we had in between 4 and 5, if there's a 4.5, then that would be continuous. But when we're counting how many did we get out of 10, well, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is the sample space. There's no 4.5, right? There's nothing between 4 and 5. So this is a discrete random variable. It is not a continuous random variable. In my guess, right, most likely, well, 5 would be, the most likely number we're going to get of the number of heads. But how many times should we expect to get exactly 5 heads? I don't know. We'll think about that. Okay, so let's try it. Let's try it. We can flip 10 coins, so we can run this code. Our binom, our first argument is how many trials are we going to do. We're going to do this 1 time. We flip. The second argument is how many coins do we flip. We flip 10 coins, and it's a fair coin, so 50% of the time it's going to be heads. And the result is we got 6 heads. Did we get what we expect? Okay, well, it's close to 5. It wasn't 5. How about we do that a bunch of times? How about instead of just doing that trial 1 time, we do 100 times? So this entry here is, we're going to do this a bunch of times, and specifically 100 times that we flip 10 coins, right? So this entry is we flipped 10 coins, we got 6 heads. And then we did it again. We flipped 10 coins, we got 7 heads. We flipped 10 more coins, we got 4 heads. So this is random outcomes from that binomial distribution. So each time we flip 10 coins and we get one of these results, each one of those results is an event, right? And the 6 here is the outcome, right? So an event is result of one trial. You flip things, you see what your result is. That is one event, right? Okay, so that's if we do this, we could do this a bunch of times, right? We can here flip our coins and see what the results are. So if we keep flipping, right, there's some of the times that we're getting 5. Doesn't seem to be too many 5s that we're getting. I expected more 5s. Are we sure this coin's fair? We got a lot of 2s. I seem to see a lot of 2s and 3s. How do we know? There's a 1, a 2, a 2. Are we sure this is a fair coin, right? So this is, there's a time that I was playing a game, playing dice with somebody. Believe he had some mystical power energy, and we're playing the game Risk, and he said, whatever dice number you roll, I'm always going to roll one higher than you. And it seemed like he kept doing that over and over, that he kept rolling one higher than me. And it was like, am I just noticing it more often because he put that idea in my head? So part of the idea of statistics is when we do random events, what you expect to happen. When we roll flip 10 coins, you expect about half the time them to be heads. Well, that's not always what happens. How can you tell if what you expect to happen doesn't happen? Is it really fair, right? So we set up our hypothesis. The coin is fair, the dice is fair, and we want to test, is that hypothesis true? Well, how can we do that, right? So that's one of the questions that we're really going to be coming at to in chapter 3. So so each time I hit this reflip the coin, it flips 10 coins 100 times, and it gives us all this data. Well, that's a lot of data. What's the ways that we can summarize this information to get it? So each one of these is a discrete outcome. It's a discrete random variable, right? How many times did we get heads, right? Keep that in mind. So one way that we can think of summarizing all that information is we could average the number of heads out of 10 coins. So repeated out of those 100 times, what was the average number, right? So here it's 4.89. We can reflip again, 4.73, 4.91. It seems like that suspicion are these coins really fair? Oh, well, this time it's above 5, and it's above 5 again, and it's above 5 again. Okay, so maybe it is actually that half the time it is below 5 and half the time it is above 5, right? So each time this is giving us the average of all of those 100 times we rolled the dice. So that's one way we can summarize it. Another way we could summarize all that data is to draw a histogram of the results. So this is, rolling a 1, rolling a 2, 3, 4, 5, 6, 7, 8, 9, so on, heads. So each time we click this reflip, it flips 10 coins, it counts how many heads, and repeats that 100 times, and then it draws the histogram here. So what would you expect? What would you expect this histogram to look like? Right? I would expect it to look something like this, right? So that it's very centered around 5 with the most highest probability at 5 and decreasing odds for each number going away from there, right? That would be my expectation for what I would expect this histogram to look like, right? Put this again. Okay, how many heads would you expect? We flip 10 coins. How many times would you expect to get 5? So we can calculate, right? How high is that, right? How many times do we get 5 heads? What's the percent of times that we get 5 heads? We could calculate the percent of times we get 5 heads out of 10 coins. So doing it 100 times, right? And we can see 27%, 23%, 26%, 20%, 22%, 20%. So it seems like when we're rolling, it tends to be somewhere in the low to mid 20s generally. Now we're getting in the teens here. Somewhere around there that we tend to get that percentage of the times we get 5 heads. R can actually calculate the exact percent of times, the densities that we should get 5 heads. If we were to do an infinite amount of times, right, instead of doing 100 trials, if we did an infinite number of trials, what percentage of the time would we get 5 heads out of 10 times we flip the coins, right? So we can use the function in our D binom. That D stands for the density. So the percentage of time you're going to get a specific number, that is the density of that number. So the D binom has 3 arguments. The first one is the number you want the density of. So here we want how many times are we going to get the number 5? How many times are we going to get 5 heads out of 10? So this asks, what number do we want the density of? How many coins are being flipped? Well, we're flipping 10 coins. The percent chance of getting heads. We're talking about a fair coin here, so there's a 50% chance. And it turns out that if we were to do it an infinite amount of times, that we would get 5 heads 24.6% of the time. So that's why we're generally close to the low to mid 20s when we're doing that before. So we can use that D binom. Here I have it set up so we can calculate the density of all the different possible numbers so you wanted to consider. So the number 0 heads. How many times would we get 0 heads? It'd be well less than 1/10 of 1% of a time that would get 0 heads out of 10. Still less than 1% that would get 1 head, and a little over 4% that would get 2 heads. Almost 12% that would get the time we get 3 heads. 20% of the times we'd get 4 heads. 5% of the time, again, we're at that 24.6% that would get heads. And at 6, well, at 6, that's the same percentage chance of getting 4 heads. Chance of getting 4 or getting 6 is the same. The chance of getting 7 heads is the same probability as getting 3 heads, and the chance of getting 8 heads is going to be the same probability as getting 2 heads. Right, so we can graph these different density probabilities, right? So this is taking those different density probabilities, right? And so the probability of getting 1 head is the same probability as getting 9 heads, and the chance of getting 5 heads is that 24.6%. Right, so this is called a probability density function. This is the PDF, right? So we can graph the PDF of getting various amounts of heads out of 10 coin flips. Now, we can add to it. This is called a PDF, and this comes from theory, right? This comes from the mathematical theory that D binom function uses. I believe in the textbook, they'll give you the exact function that the D binom function is using to calculate the densities at this, but this is coming from theory, so we can ask, and of course, this theory is saying this is what you would get if you were to flip 10 coins an infinite amount of times, right? We can ask, what happens in reality, right? So we have our PDF, this red line. This red line is the PDF, the probability density function that's coming from theory. And then the empirical, the ePDF. So E here stands for empirical. What do we actually get when we try it? So here we can set how many number of trials do we want to do. So if we do 5 trials, that, how many times do we get various outcomes? In this case, we got, it looks like we got 9 once, 8 once, 6 once, and 4 two times, right? Well, that doesn't look like the PDF at all, right? If we increase our number of trials to 10, well, that's looking a little bit more like our PDF, our probability distribution function. So we get to 20, still, not really looking like the probability distribution. But as we increase the number of trials to 50, to 100, 500, 1,000, right now at 1,000, are empirical, right? The dark gray is the empirical. It's what we're getting from simulation, from the computer simulating flipping coins. Whereas the red line is gone from mathematical theory of what we would expect to get of doing it 1,000 times, right? So as we do more trials, it gets more and more close to the theoretical distribution. At 10,000 trials, right? We have that the ePDF, the empirical PDF, right? It is a discrete random. We have a large number of trials. The empirical probability distribution function looks very much like the theoretical probability distribution function. When we have a low number of trials, there's less likely, it's very unlikely, that it'll look very much like the probability distribution function. But as we get higher and higher amount of trials, the distribution approximates, gets closer and closer to your probability distribution function. We can also think of the cumulative distribution function. So if we took the probability of getting 1 heads, and then the probability of getting 1 heads or 2 heads, the probability of getting 1, 2, or 3 heads, we're taking the cumulative probabilities here. So with the cumulative probabilities, it is always going to be increasing. And when you're getting at 5 heads, at that one number, going from 4 to 5 heads, we're going to increase the probability by that 24.6% chance. So it is going to be the steepest at 5 heads, whereas at the very end, right, the probabilities of getting a 0 or 1 was, like 4%, and likely the probability of getting a 9 or 10 heads was about 4%. So those are going to be very flat, where it's going to be steepest in the middle. So this is a cumulative distribution function. It's measuring at each point the probability of getting this number and anything lower than it. So again, this cumulative distribution function, this is coming from theory, and then you can see how it matches up with the empirical cumulative distribution function. So the black line is the empirical cumulative distribution function. And again, if you have very low number of trials, there's not much guarantee that it's going to look very much like your empirical, or your empirical look like your theoretically one. But if you have a high number of trials, again, it gets almost to be matching exactly the theoretical cumulative distribution function. Okay, so we've talked about our probability distribution function, our cumulative distribution function. We've talked about the empirical versions of each of those. We've gotten the idea that the outcomes here, right, is in each one of the trials, what you get in a trial is the outcomes. The probability, I think we already get the idea of probability, the probability of getting ahead. Sample space is the possible outcomes that can result. Each time you do a trial, that is an event. A discrete random variable is when between 2 outcomes, there's another possible outcomes between those 2 outcomes. Or sorry, there's not always, for discrete, there's not always something in between 2 possible outcomes. So between getting 4 heads and 5 heads, there's no option between those 2. So those are discrete. But if you're calculating what is the mean out of 100 trials of how many times you get heads, well, then it might be 4.5 or 4.52, right? That is a continuous random variable. With a continuous random variable between any 2 outcomes, there's hypothetically another number that you could get that's between those 2 numbers. And so these are all the concepts in section 2.1.